We're going to get started in 1 minute, so if you guys can find a chair and start sitting down. Okay, so let's get started. It's noon. We are being streamed out in video, YouTube, and the link was sent before actually, so you have it in the attendees list. If you want to follow that or distribute to someone that wants to follow this live, that's possible. As I said yesterday in the plenary, this is part of a series of presentations that they are organized on Thursday lunch, and the host typically organizes a presentation about a technical topic that is relevant to the IETF. In this case, we were thinking, and coming from Ericsson is we have a lot of radio competence, radio products, radio offerings. We thought that 5G would be a great topic, so I hope you guys are interested in it. So once we decided what topic was going to be the one for this presentation, I was looking for someone that could actually give this presentation to a technical audience. So I managed to convince Eric to come here. Eric is one of our best radio experts. He has been deeply involved in 3G, 4G, LTE, and now he's actually involved in all the activities going towards defining what 5G will be and actually eventually standardizing those aspects. So Eric works for Ericsson Research. He's one of our senior experts. Senior expert is basically the top technical rank we have in the company. So let me welcome Eric, and the floor is yours.
Okay, thank you. Hey, thank you. I'm happy to be here. This is kind of the light is not on. Yeah. Great. Then I skip it. Can I use this instead? Okay. Better. So thank you very much. It's very nice to be here. As I said, you are this kind of legendary group. I was in 3GP before close to 10 years, so I recognize these kind of gigantic rooms with a lot of people. So I will talk a little bit about 5G, what it is, what's happening, etc. And when it comes to what it is, I mean, it's not really anything yet. It's just a lot of discussions about what it may be. But I will give a little bit about view, what we believe it will be, also hopefully then reflect what if other people, other companies, other organizations have somewhat different views. A little bit also what happens in the world. But I will a little bit start with kind of providing some kind of background. You have probably seen this picture. It's at least some of you. It's when the new Pope was to be announced in 2005 on St. Peter's Square. There was a lot of people there, and you can see there are probably most of these people have a mobile phone in their pockets, and some of them are even so bad as they are using them when the new Pope is being announced. But of course, this Pope, he was just there for a few years, and then last year there was a new Pope, and then it looked like this. And you can see there's same place, probably a lot of the same people, but there's one major change. I mean, it's not lights they're holding in their hands; they're mobile phones. So and it was, as I said, I mean, it was probably so. In this case, most people here probably have a mobile phone in their pocket at this place because at this time because. I mean, in 2005, most people in Europe have a mobile phone. But they are using it in a completely different way nowadays. They are not using it as a mobile phone. They are using them to take photos, they are using them to share data, etc. Of course, this picture just indicates that they are using it to take photos. I mean, it doesn't really indicate that they're using it for any kind of communication, which would not be very good for us. But they actually are. And if we may look at how you use a mobile. Once upon a time, it was really called mobile telephony, and I think up until around 2009, it was really the voice services that was dominating in the mobile phones. But around, from 2007 or so, people started to use them for data, and just continue, and now it looks like this. And essentially, the mobile telephony is nothing nowadays. It's only mobile data, and it just goes on and goes on. And of course, it's a lot of laptops, tablets, etc. But the vast majority is really people using their smartphones, and they're using it for video, sharing data, and things like that. And this will hopefully continue, and this is, of course, what we need to develop new technology for. So that's one reason why we're looking into 5G. But I think it's also interesting that we talk about 5G, and of course now we know that nowadays we have 4G, we call it LTE, and there's also of course earlier technologies. And there's a lot to talk about 4G. But if you look at it, how it looks, 4G is really a small thing today. I think it was actually second generation is still the biggest technology being used today. And it was actually, I think last year, where finally the amount of devices that only support second generation, GSM mainly, start to shrink. And even if you go up to 2019, 2020, where we actually start to talk about everything, when we will have 5G, LTE, 4G will still be a smaller part of the technology. I think this is important to have in mind, that we start developing technology and we even start to deploy the technology long before they get some kind of major impact. But that also means that in the same way, 4G is very small today on the market compared to second and third generation, but we still start to develop 4G technology almost 6, 7, more, I think almost 10 years ago. And that, of course, implies that we need to start to look into 5G now. So what is 5G? And then if you start to look historically, and believe it or not, I was actually working on even the first generation in the 1980s. I was very young by then. My father was making base stations for the NMT system, and I was forced to work with these in the summer. Essentially doing some kind of adjusting some filters, meaning that I was running to the sauna, in with the filter and out again, and there was a measurement, twist some stuff, put it in the freezer, and it was a big piece of equipment. Up again, do some measurements, turn some knob. I had no idea what I was doing. The only thing I learned by then that I would stay out of all kind of product stuff and stay at research. But if you had the first generation was really what brought us mobile telephony, of course, in the first place. And then with second generation, it's mainly GSM. Of course, we got mobile telephony essentially for everyone in the world. And then with third generation came mobile broadband. And now it would be good to say that with fourth generation, we will have mobile broadband for everyone. But honestly, if we look how it looks in the world today, we will probably have mobile broadband for everyone already with 3G. At least with everyone. So really, what 4G is about is just providing, on a high level, it's just providing bigger and better mobile broadband. High data rates, high capacity, and one more important thing, I think, with 4G is the first time we really get a kind of one single global technology. Up until including 3G, we all have different technologies that are partly dominating in different parts of the world. But with 4G, it's really the entire world going to the LTE. But then, of course, is the question, what are we going to have? Why are we going to have 5G? Is it just bigger and better mobile broadband? Or even bigger, better mobile broadband? We don't really see it like that. And I know that my colleague mentioned this network society already yesterday. So we really see 5G as some kind of long-term enabler of the network society. And of course, the network society is a very fluffy thing, and there are extreme. This sounds very fluffy here, but it's actually the least fluffy definition I've seen. You should see them. My bosses, they have even more fluffy definitions. But I really see it as at least on some kind of vision level. So it's about having access to information and sharing of data anywhere and anytime to anyone and anything. And I think that there are some key words here. It should really be anywhere and anytime. It's not so that one should have access to data or access to wireless communication only in cities, etc. It should truly be for everyone. It should be like as ubiquitous as air in some sense. And the other thing is that it's not only in the future for anyone, it's also for anything. So it's all about these kind of, let's say, what you call communicating machines. It's not only about humans communicating, or everything being able to be connected. There are, I mean, more relevant things, and sometimes there are less relevant things. Things like saying my umbrella should be able to call the weather service safe to find out if I need my umbrella today and things like that. But fundamentally, it's about I think that one should have possibility to connect. It should be like obvious how to connect anything if you want to. Then it's, of course, I mean, if you look at historically, I mean, every generation we had has really been like associated with a specific new technology. So second generation was GSM, third generation was wideband CDMA and CDMA 2000, fourth generation was LTE. And there will clearly be completely new technology for 5G. But at least when we talk about 5G, we don't really want to see it as kind of that technology driven, saying that, oh, we need new technology, and let's call it 5G. I would rather like to see, I mean, 5G is some kind of solution, a problem and its solution. So 5G, in my view, 5G is all this thing about how do we solve this entire network society, or the wireless access part of the network society. And of course, that will partly be quite a large extent be solved by the technology we already have today being evolved. And together with that, they will of course develop new radio access technologies. But we would really like to see this entire package as the 5G. So 5G is not only the kind of new radio access technologies. Now, in the end, of course, we don't know how things will turn out. I mean, market in the end will decide what we call 5G. But at least today, we would like to rather focus on this kind of the problem we want to solve, rather than that we should have a new specific new technology. And as I said, I mean, at least to us, it is a lot about this kind of new type of applications. It's not only about getting bigger and better mobile broadband. If we were only interested in getting bigger and better mobile broadband, higher data rates, more capacity, honestly, I mean, I think we would do quite well by just evolving the LTE as we have it today. We can't do any real magics here. But we would really like to see this overall 5G as some kind of platform on which any kind of wireless application can be implemented. A wireless application that we can envision today, and also a wireless application that we cannot even envision today. So of course mobile broadband will continue to be extremely important. I mean, and that's the kind of application that we know how we make money from. We know that people want it. We know that people will always want higher data rates. We know that traffic will always increase. But there's also a lot of new type of applications that the wireless application one can envision. I mean, wireless applications for the to enhance the electrical grid for or other types of critical infrastructure. Wireless communication for traffic safety and control. Wireless applications more for the smart buildings. Wireless applications, industrial processing, you name it. All these kind of people, what we call wearables, people have communicating devices all over their bodies. So at least I think the key thing for us is really that, and I think that's a message that we hear from most other players as well, that 5G is really much more than just even better, even faster mobile broadband. But that also implies, I mean, here comes the really big challenge, I think, for the future, that we are implying we're facing a much wider range of requirements and challenge targets, or a much wider range of requirements and challenges. If we look historically, I mean, fundamentally, we have always wanted to have as high traffic capacity as possible with as good quality as possible. And quality has been partly changed. I mean, once upon a time, quality was really voice quality. So it was really about how can we squeeze in as many voice users as possible for a given voice quality. And then when mobile broadband started to dominate, the capacity was still the same, how many users as possible, but the quality partly was changed then to to data rates. It was really about how do we squeeze in as many users as possible with a certain data rate requirement, a certain data rate target. And I said that will continue to be important, and we will continue to enhance that. And we will, one requirement for the future will be we want even higher data rates, and I will come back to that a little bit, but we always want higher data rates. When we talk about them, we never understand what we're going to use them for, and then once we've had them, we can never understand how why we didn't want, how we could live without them. And we will have to support extremely high traffic capacity. I mean, there are different estimates of that. People sometimes say 1,000 times more traffic in 10 years. That, of course, depends. I mean, you can't really say how much traffic you're going to say, except how much traffic demand there will be. And then, of course, it depends if we can support or not. And I don't know if it will be a factor of 1,000. Even if it's a factor of 100 times more traffic in 10 years, it's kind of really a big number. So those kind of requirements will continue to be very important. But if we now want to support or have an overall wireless access solution that can support all these kind of new services, some of which we can't even anticipate today, we have to ensure that a lot of other requirements can be fulfilled. So we have to ensure that our network can provide extremely low latency, for example. They are already doing quite low latency. But there are some of these applications. If we want to have, for example, I mean, the overall 5G wireless access solution also has the kind of backbone for traffic safety, etc. It may have an even lower latency. Maybe we're talking about sub-millisecond latency in the radio interface. We have to support an enormous amount of devices. Today, maybe we have like 7 billion mobile phones. There are people talking about, within 10 years, 50 billion mobile phones with all these kind of new machine type applications. And there are even people talking about 500 billion devices. So we have to ensure how can we support such an enormous amount of devices in our network in an efficient way. We have to support or enable devices that have extremely low energy consumptions. Of course, we have always been targeting very low energy consumption devices to have long battery life, but we then talked about like, once upon 10 years ago we had like 2 weeks of battery life. Now it's actually been degraded quite a lot with all these kind of smartphones. Now I probably have to recharge my phone every day, but that's typically fine. But in the future, maybe we want to have these kind of devices sitting up on the wall, and they should sit there for a year or several years without being recharged. So we have to ensure that we can have devices that have extremely long battery life. And we also have to ensure that we can have devices that have extremely low cost, perhaps just a few cents, for these kind of billions of devices sitting, sensors, etc., sitting everywhere. And there may be other cases where we need to have extremely reliable connectivity. Of course, we believe that our networks are extremely reliable all today. But if we want to have it for traffic safety, if we want to have it as a part of a critical infrastructure systems, etc., we may need to have extreme reliability on a completely different level. So it's kind of lot of different new type of requirements we are seeing. And of course, it's not so that all of these have to be fulfilled at the same time in the same device. I mean, we can't have like 10 gigabits device cost a few cents. But overall network solution should allow for devices that support extremely high data rates, and at the same time allow for devices that can be extremely cheap. And of course, in the end, we have to ensure that all of this is affordable and sustainable, which is just nice words for saying that we want to have, of course, low cost and low energy consumption. And that comes, I mean, in some sense, just from this kind of much higher traffic. If you take, say in future, we expect 100 times more traffic. We can't expect that people, because in the end it will be the people that use it that will pay for everything, that they will pay like 100 times more money for their mobile service. That would be fine if they could, but they won't do that. So of course, we obviously have to have much lower cost per bit we deliver. Similarly, actually, honestly, I mean, the energy consumed in the mobile networks today, all the energy consumption is a substantial cost for some operators. I mean, the overall energy consumption is a very small part of the overall world energy consumption. But if we would increase our energy consumption a factor of 100, we would have major problems, because they would probably exceed overall, close to the overall world energy consumption. So we obviously, if we're going to increase the traffic by a factor of 100, we need to ensure that we can deliver every bit, like an extremely small fraction of the energy compared to today. So I mean, those things, I mean, cost per bit and energy per bit will be extremely important in the future. A little bit about data rates, because we always talk about data rates when it comes to every generation, for the new generations. We've always done that. And we're always talking about peak data rates, and as I said, first of all, we never understand if we're really going to need them, and then after a while we realize we needed them. And there is actually an interesting story there, because I have a person at Ericsson, I think he's retired now, but he was a really clever engineer. He was also a fantastic inventor. I think he was on the 4th place on the world inventors list. And that list was like headed by Edison, so it was high-level guys there. And when they were specifying 9.6 kilobits per second data rate for GSM, he said that was a completely different exercise, because he couldn't imagine that anyone would ever need more than 2.4 kilobits per second in their mobile phone. And he was wrong. So we have a generation, we have higher data rates, but the problem we always have is we're always talking about these kind of peak data rates, which is some kind of theoretical number. I mean, we talked about 3G, 2 megabits. No one got 2 megabits when 3G started. Then came HSPA, 14 megabits. Then come LTE, 100 megabits. Then came what we call IMT Advanced, which is essentially 4G, where we talk about 1 gigabits per second. Actually, there is a requirement on a 4G technology to support 1 gigabits per second peak data rate. And I guess no one here or anyone has ever experienced that kind of 1 gigabit data rate anyway. And probably no one has ever even missed it. What you're missing is that you don't have LTE coverage, or that you just get a few megabits instead of a few 10 megabits. But we always come to this kind of extremely high peak data rates that are in practice only achievable if you stand on top of the base station and probably put the antennas next to each other. Still, when it comes to 5G, I mean, we will talk about 10 gigabits per second data rate for 5G. It's impossible to stop. There are discussions already in ITU about targets for 5G. I was trying to say that we don't care about peak data rates, we only care about achievable data rates, and people still say, but we need to say 10 gigabits per second because it's good for marketing and it looks good on slides. So there will be some kind of requirement on 10 gigabits per second, or at least, there are even companies talking about 50 gigabits per second for 5G. And that's fine, I mean, and then we should understand, well, of course, we can achieve that in certain situations. If you make an extremely dense deployment, very, very small cells, so that we have like essentially a fraction of a user per cell, then it's possible to achieve. But I think we should be much more focused on how can we achieve like a few hundred megabits in general available in suburban and urban environments. In my view, that's much more important. And perhaps even more, if you truly believe in this wireless communication should be available truly everywhere, then how can I ask ourselves, how do we achieve just a few megabits, let's say essentially everywhere on the globe? And when I say essentially here, because that means, I mean, okay, I don't care about on the bottom of the sea, etc. But I mean, if we can provide a few megabits data rate over the entire African continent, into every small village, etc., that could probably change people's life much more than if you can achieve 10 gigabits on Times Square in New York or something like that. So at least from our point of view, I mean, we will talk about 10 gigabits per second, but I think it's much more important to try to see how can we achieve these. And actually, these are also much more difficult problems. Achieving 10 gigabits peak data rates is very simple. You just specify on paper that you have extremely wide bandwidths. No operator will have that bandwidth, but you write the specifications that is supported, and you can say, okay, I have 10 gigabits per second peak data rate. How we achieve 100 megabits of generally available in urban, suburban scenarios is much more difficult. Because then we're running out of power, or we don't have sufficient power for our base stations, etc. So that's a much more relevant problem. I think that is one thing we should focus on a lot on when it comes to future radio access. When it comes to traffic capacity, As I said, there are talks about 100 times more traffic in 10 years, 1,000 times. They even talking about 5,000 times more traffic. Whatever we talk about, it's a big number. We can only, I mean, that's fundamentally very simple. We can achieve this in 3 different ways with 3 different tools. We can put in more equipment, or we take another direction. We can make better radio access technologies so that for a given amount of spectrum and a given amount of equipment, we get more capacity. That's what we've done until now, and we've done it very well. The problem with doing it very well is that there's not so much potential left on that one. There are certain things we can do, but we are start to get somewhat close to what is theoretically possible. So the other approach, of course, is get more spectrum. Spectrum is not that, much available, especially on the lower frequencies, but it clearly implies that we will have to go to higher frequency bands in the future to get more spectrum. Still, I mean, we cannot get 100 times more spectrum from today. We can perhaps get 5 or 10 times more spectrum today if we are extremely lucky. So we'll get very far from the 1,000 times capacity. So, in the end also, we have to ensure that we have much more dense networks. We have to have much more infrastructure out there. Much more small cells. And I mean, this really in this order that the kind of gains will come. The biggest gain will come from densification of our networks, then more spectrum, and then in the end getting more better technology, which may give us like a factor of 2, a factor of 3, up to a factor of 5, perhaps, if we are extremely lucky. But then we should also have in mind that to get more spectrum, for example, to get spectrum at higher frequency bands, we may need new technology to be able to do that. So new technology really comes in the 2 other cases as well. I mean, if we want to have very dense networks, we have to look into technology solutions for very dense networks. So it's not so that it's not so that technology is only kind of in the lower line here. I mean, the technology in itself is in the up in the densification and new spectrum as well. But now I already talked about high data rates, extreme capacity, and that is really kind of bigger and better mobile broadband, which I say was not the only thing that 5G is about, but it is still one part of it, of course. Because we know that people will want more high data rates, there will be much more traffic, have to support that. But the other one is really this about network society, machine type communication, whatever you call it. And the problem with that is, of course, that we have no real clue what it is. There's a lot of visions about possible applications, and honestly, when people start to come with examples, quite often they start to become quite weird, and you can't really believe in them. So it is really so, I think, and I think the problem is a little bit, before we have the network there that can support these new type of services, new services will not come. So it's a bit of chicken and egg problem. So we really need to design radio interfaces like that can support new applications that we do not really know yet what they will be. We can only have some kind of rough ideas about what the requirements are. And there will, of course, be a lot of different possible applications. We have at least tried to divide them into two main groups. One thing is we call like a massive machine type communication, which is this about extremely many devices that have to be extremely low cost, extremely low energy consumption, probably need coverage everywhere, but the data rates are not very high. But also that there will be like a truly massive number of devices. That's like one area. That can be all these kind of billions, tens of billions, perhaps hundreds of billions sensors out there. They should not cost anything. We need to have networks that can support extremely cheap devices, extremely low energy consumption, enormous amount of devices. And as I said, the payloads, data and payloads are typically very small. So it's not so that they will perhaps generate a lot of traffic, but we have to support them. Which also makes them potentially a good business case for the operator, because if they don't use any capacity, does not really cost the operator anything. So if the operator can just show a few dollars a year for that, but there's no cost associated with it. On the other hand side, we have what we call more like critical machine type communication, where we have applications which probably may require extremely low latency and extremely high reliability and extremely high availability. So it could be this kind of communication in industrial processes, communication for traffic safety, communication for critical infrastructure, where of course like the device cost is not really a critical issue, or the device battery life is probably not a very, energy consumption not a very critical issue. I mean, if you put your device in a Ferrari, it does not really cost, that matter how much the device costs and how much energy it uses, because I mean it's still like completely negligible compared to the Ferrari. So, but I think a key thing here is really that we only need understand these kind of high-level requirements, but we don't really yet know what will be the applications. And most likely we will not know the applications until we have the networks there. I usually sometimes actually refer to you guys when I talk about this, because I guess it's a little bit about you guys. Well, I don't know, maybe it was your grandfathers so that invented the internet once upon a time. I guess you had no clue about Facebook and these kind of things, and you probably couldn't imagine it. And still one made internet in such a flexible way that it was actually possible for people to later on invent Facebook, invent Twitter, everything of these kind of applications. And no one would have been able to come up with Facebook if internet was not there already. So I think that there was no way of anticipating Facebook. So I think it's somewhat similar here. I mean, we have to design networks that can support yet, how to say, unanticipated services. Okay, so now we come to a bit of technology. What is now? There must be some technology in 5G. And there's, of course, a lot of things out there. I mean, I have here just listed a few things. But I want to talk specifically about the first two, actually, about one thing about the spectrum. Because if you look at spectrum, I mean, today we are in mobile communication, we're operating from around 1 gigahertz up to around 3 gigahertz spectrum. We started with lower and go slightly up or higher all the time. But I think one thing that is clear, in the future, for 5G, we will extend to much higher frequency bands. There are discussions about going up to close to 100 gigahertz spectrum. But we should remember that can never be like the whole solution, because higher frequencies are like fundamentally worse. I wouldn't say fundamentally. There are problems with high frequencies, which make them, they only work in certain places. We still always need lower frequencies to get like full area coverage. So we will get higher frequencies as a complement to the lower frequencies to provide extreme traffic capacity, because there's of course much more spectrum up there, and extreme data rates, because we can get much higher wider bandwidth up there. The problem, as I hinted, I mean, there are propagation problems with higher frequency bands. Let's say, like, fundamentally, sometimes you say, oh, higher frequency bands, they are fundamentally worse. They are, the propagation loss goes up with the square of the frequencies. That's not really true. That's always based on assumption that if I increase my frequency by a factor of 10, I reduce all my antennas a factor of 10 in that dimension, a factor of 10 in that dimension. Because, I mean, the wavelength goes down, so everything becomes smaller. And it's quite obvious, if I go up in frequency factor 10 and I reduce my receive antennas area with a factor of 100, of course I capture less energy. But if I don't do that, I mean, I don't get that loss. And honestly, if I always also keep if I keep my receiver antenna fixed as I increase the frequency, I don't get that loss. And actually, if I keep my transmit antenna fixed as well, then I actually gain by going up to higher frequencies. And that's why we are typically used, because you get like you can like pinpoint the transmission in a certain direction, get all energy much more directive in a certain direction. And that's of course the reason why in all these kind of microwave links, etc., we're using higher frequencies. But that's only if you have this kind of microwave link line of sight stuff, or millimeter wave radio link line of sight stuff. In practice, higher frequencies have certain problems. We typically base our system on the fact that we hope that radio waves goes around corners, for example. We don't want to go around the corner and lose connectivity completely. But as we go up in frequencies, radio waves goes less and less around corners. That's quite obvious. I mean, if you go sufficiently high up in frequency, I mean, you come into like visible light, and we know by experience that visible light typically do not go around corners very well. You can't really look around the corner. Similarly, our systems typically is based on the kind of assumption that radio waves goes through the walls. That also gets worse and worse at higher frequencies. It's actually a problem more than at today's frequency, but it gets just worse and worse. So we get problems with indoor coverage. We could have got problem with due to rain, but that's not really a problem if you have very short range. And it's another problem if I hold my phone like this. I mean, radio waves, they won't even go, high frequency will not even go through my hands. So at least we see higher frequencies. They will suit very well for very short range communication. Picocells, etc. Small cell deployments. And that's of course where we will have those anyway, and where we need a lot of capacity and where we need a high data rates. So they are very suitable to provide very high data rates and very high capacity in specific areas. Another thing about spectrum, if you look in our systems today, let's say in the cellular business we are using what we call dedicated license spectrum. The spectrum specifically for mobile communication, and the spectrum is licensed to a certain operator, pays a lot of money for it, and is, exclusively have access to that spectrum. Very good, provides opportunity at least for having very good quality. And it's actually quite a very efficient way of having spectrum. On the other side, of course, we have the unlicensed spectrum, and for Wi-Fi, and that, of course, all today is becoming like a complement also for the mobile operators. More and more mobile operators, they have both cellular network and Wi-Fi, and there is actually already now proposals for not just having Wi-Fi in unlicensed spectrum, but actually extending LTE into unlicensed spectrum. That would then be another way for a mobile operator, an LTE operator, for example, to make use of unlicensed spectrum as a complement to the dedicated spectrum. But in the future, we will probably see much more of these kind of spectrum sharing methods. Not dedicated spectrum like we have today will continue to be some kind of backbone for operator, providing kind of high quality spectrum for high quality connectivity. But it is also a fact, I think, that if we go to more and more dense deployments, having spectrum dedicated to a certain piece of spectrum dedicated to a certain operator may not be the most efficient thing. I mean, just envision, I mean, saying they have 80 megahertz spectrum, every 4 operators get 20 megahertz each. In the future, if you have this kind of extremely dense deployment at a certain place, it may be so that at that specific place, in that specific room, actually only one operator have a customer or a user in that room. And then if you have this kind of dedicated spectrum, that user will only get access to 20 megahertz in that room, and the other 60 megahertz will be unused. It's quite obvious that in that specific case, at least, it would be more efficient if that specific user could get access to all 80 megahertz. So in some way, either unlicensed spectrum or things in between. I mean, it could be licensed spectrum, but it's licensed to a set of operators, or spectrum licensed to one operator, but that other operators can use in some kind of secondary usage. A lot of these things are being looked into. Different ways to, I would say, specifically use spectrum more efficiently in these kind of extremely dense deployments where traffic will be much more, variable. So I think that's another area where we will kind of extend these cellular systems into more different ways, means of spectrum sharing. And then going back to this picture, there's a lot of other areas. I said the key tools to get higher capacity in the future will be more spectrum and more dense networks. I think this entire idea about advanced antenna technologies, putting in more antennas at the cell site, which is somewhat similar to densification. Instead of putting in more equipment by putting out more base stations, you keep your base station, but you put in much more antennas at the base station. That is definitely an area where a lot of work will continue to be done to provide high data rates, better coverage. Different means for coordination between networks. Today, if you operate like a macro network and a low power, small cell network below, I mean, on the radio side, they are quite, unrelated to each other, or not very interworking with each other. In the future, there will be much more such interworking. Devices connected to multiple layers at the same time, devices connected to multiple base stations at the same time. Base stations cooperating to avoid interference, all these kind of things. That's also an area I think we can gain a lot. Ultra-lean design is also something that is talked about a lot. It's actually one of the few things I'm a little bit unhappy with LTE about. LTE is a very good technology, but it has a small problem. Because even if you talk about the kind of, we need all this kind of capacity, it's a fact that most people actually don't believe this. Most cells are actually empty, typically empty. What I mean by this is not, of course, it can maybe use that, but essentially, I mean, at most instants in time, there is nothing to transmit from a certain base station, because there is no user there, or because at that specific time, no user wants any data. And another way of expressing it, we actually put out a lot of base stations that is put out to cover this area, even if there would be a user there. This is, of course, not true for the center of the big cities, but if you look at the overall set of base stations we have all over the world, most of them are, on average, actually silent. Or they should be silent. The problem is that we have designed the technologies actually so that base stations, even if there is no user there, still transmit a lot of garbage. Pilot symbols, reference signals, broadcast information, etc., which will impact, both cause a lot of interference and actually cause a lot of extra energy consumption of base station. So in the future, we really should ensure that we have base stations that are, base stations should essentially, they should transmit when there is something useful to transmit. Or base stations should transmit when there is someone there listening to what they transmit. I think we will get a much more, today we have like the access link, which is from the base station out to devices. But people often forget that we also have a very important link going down to the base station from higher up in the network. And for example, people talk a lot about these kind of small cells. They will provide enormous capacity benefits, enormous data rate benefits, and they can show in simulations they get enormous capacity. But they quite often forget. They find out they can get a lot of bits out of the base station, but they often forget how to get the bits down to the base station. We can't assume that there will be optical fiber down to every small base station everywhere. I think actually wireless backhaul will be an important part of it. Wireless backhaul is important already today for our big macro base stations. We have microwave, millimeter wave links going, line of sight going to the base stations. But it will be even more important in the future, and then we will have like base stations down on street levels. It will not be line of sight anymore. And then we come to the question, why do we see it's like we have one radio access technology to get bits from up here down to the base stations, and another radio access technology of getting bits from the base station down to the device? Why don't you use the same technology? Why don't share the spectrum? Why do we see these two links as two different links? Why don't we see it as it's fundamentally a solution of getting here to here, from here to here wirelessly? Why you did one hop or you do several hops? We will of course end up in the end in some kind of multi-hop solution, but that's at least what I think. I mean, we'll see much more kind of overall wireless access solution, including both the access link and the backhaul link. Part of this is also that we will, or we may, we may have more into kind of device-to-device communication. That's something that is actually worked for all of the LTE in LTE today. I don't know if it's how successful it will be. It's quite tough to get to press in device-to-device communication in an already done technology. But I think in the future we should look at a much more flexible structure where we have base stations, we have devices, and devices communicate with base stations. But also if two devices want to share information, they can also communicate directly with each other. Or one can use one device as a relay link to reach another device that's out of coverage. All these kind of things. I think we will have in that sense, a more integrated solution, which perhaps even treat base station devices more on a little bit equal footing. Yeah, good. I'm all in the bed. Time schedule. We are still in the research phase on 5G. There are discussions about standardization activities. When going to ITU, I start to discuss about requirements, which is of course kind of prerequisite for them people to be able to do standardization. Everyone talks about 5G being available around 2020, somewhere in that range. But as I believe, 5G in some sense will be consist of new technology and LTE, evolution of existing technologies. I see them more as, it will be more, glide into 5G. It will not be able to say that this day 5G happened. So that also means the big activities we have today, they are really on the kind of research level. We have Europe has a good history of having these kind of European Union-sponsored projects. We had something called Frames that led to 3G. We had something called Winner that led to 4G. A few years ago, actually, we at Ericsson, we saw that maybe it's time to do something similar for 5G. So we started what's called the METIS project, which is a project, the target of doing research on 5G technology. All the kind of big manufacturers are there, big operators. Interesting enough, also like a company like BMW is there. That also a little bit indicates these kind of new applications. BMW, they are not interested in 5G, not only because they are interested in how to get information into their car and out of their car. They see like their car is a big thing with a big battery in it. Typically often parked a place where there are a lot of people. How could their car be part of the overall wireless infrastructure in the future? Could you serve as a relay point, not only into the car, but actually around the car? So that's one activity. Of course, Asia is very active as well. China has different activities. IMT 2020 promotion group is more of a discussion group. They have a big research program very similar to METIS, where also non-Chinese companies like Ericsson takes part of this. Korea is very active also in 5G. Of course, Samsung is very active. There was something called a 5G forum. So once again, I mean, very active in promoting 5G. Japan, of course, historically been very active on this one. The US, not of course the same kind of history, or the North America, not the same, I should say North America than in Canada. They, of course, do not have the same kind of history in government-sponsored projects, but there is a lot of very important university work going on in North America on 5G. Just to mention, for example, New York University are very strongly promoting these higher frequencies, doing a lot of measurements, trying to argue that higher frequencies are definitely feasible for 5G in the future. I'll skip that slide. So just to summarize, for me, I mean, or for us, 5G is really the overall wireless access solution of the future, let's say beyond 2020. So it's not just a new technology, it's like a combination of new technology and evolution of existing technology, trying to solve this entire network society. And as I said, I mean, it's not only mobile broadband, it's really kind of, I would like to see a platform for which any kind of wireless application can be implemented. At least a kind of much wider range of requirements. Latency, cost, reliability, data rates, all these things. Wide range of technology components, of course, and still time money. We are still, we have been in the research phase now for several years. Perhaps we start to see a little bit the end of at least, or see the end of us going beyond the research phase. There are discussions starting about how standardization could be done. What could be possible timelines for 3GPP? What could be possible timelines for ITU? But nothing is decided yet. But there seems to be kind of fundamental consensus that deployment of 5G should be around 2020. There is a little bit kind of, Koreans want a little bit earlier. For Korea, it's very important to have something for the Korean Winter Olympic in 2018. Japan is very fine with 2020 because there's a Summer Olympics in 2020 in Tokyo. So the Olympics plays a big role here. But I would say 5G around 2020, that's a good kind of date for it. Okay, thank you.
A couple of questions.
Yeah.
Scott Bradner, this is all carrier wireless, right? It's not enterprise. What's the possibility of some of the same technology being used in enterprise wireless? It's certainly the carrier's dream to be the only purveyor of connectivity to the world, but that's not a lot the way it works today.
I'm not sure it's only for carriers. Of course, I mean, from the kind of background we have, we see a lot of operators in front of us. But I think especially many of these new applications, they could definitely be made, how to say, rely at least on part of new type of business cases or business situations. So I wouldn't say this is only for the operator, but of course, I mean, from our point of view, we see the operator will continue to play a very important role in the future. And I think it's important to have in mind that when I say here evolution of existing technology, note I don't say only evolution of LTE here. Existing technology include also other technologies, wireless technologies here, definitely.
Yeah, hi. I had a couple questions. One was about NTT Docomo, because I was at Mobile World Congress at their booth. They had a demo on NOMA, non-orthogonal multiple access. I wanted to hear your take on that. Second question is related to what you were saying earlier about NYU, the Polytechnic professor Theodore Rappaport and his research. I mean, there's been some contrarian opinions on that as far as safety of higher frequencies, and maybe you could give us some thoughts on that. Thanks.
On the NTT Docomo NOMA, I mean, my list here is not complete. That's a dot there. NOMA is like one more detailed technology NTT Docomo proposed. May give some gains. I haven't studied much in detail. I don't think that's not the kind of technology that's kind of thing that may give like 30% more capacity. So it would provide something, but it's far from the 100, I think. So it's just like one component. When it comes to higher frequencies, as I said, Ted has been very good in promoting high millimeter waves. He's very good in promoting things. Higher frequencies will happen regardless if you believe it or not, because it's gone so far now. So as high frequencies will happen, I think it's good that will happen. They will be beneficial in certain scenarios, but high frequency is not the same as 5G. It will just be one part of it. It's not like, I mean, I'm not as enthusiastic as Ted is when he says that, he feels like it's a paradigm shift in the mobile communication business. It's bigger than compared to when CDMA came. He always gets religious, but higher frequencies will definitely happen. I think they will serve a purpose in the kind of extremely dense deployments to get extremely high data rates, extremely high capacity. But it will not only be 5G. It will be one component of 5G. Yeah.
Yes, my name is Charlie Perkins. My question, I think, is related to Scott's. Right now, I understand that about 3/4 of the wireless data is carried over 802.11 unlicensed spectrum, and I wondered if you see that reverting back to licensed spectrum carrying the majority of the data. And a related question, I wonder if you see, you mentioned very low cost, very low device cost, and presumably data cost. Do you think that we're going to see a continued decrease in the data cost so that it might essentially compete effectively with 802.11?
On the last one, you're almost getting into kind of business question. I'm at research. I'm not a capable answer. On the first one, whether traffic, of course, clearly a large part of the wireless traffic today goes over Wi-Fi. Whether traffic will come back to it, I mean, let's see it like this. Traffic, anyone expects traffic will increase enormously in the future. So that means that traffic will increase enormously, both in the cellular networks and the Wi-Fi networks. Whether to what extent the fraction will change or not, I don't know. But I mean, I'm quite sure that wireless traffic will traffic in the cellular networks will increase dramatically. And honestly, I mean, for us, I mean, it's not such a big difference because operators, they are running both networks. So it's more like whether traffic goes over licensed or unlicensed spectrum. So it's not such a big thing for us. But I think, I mean, traffic will increase all over the place and all types of networks. When it comes, if the cost of data will go down, the cost of data cost per bit will definitely go down. I don't think one should expect that one will be able to pay much less per month today in the future than today. Because all today, I guess one pay an amount like similar to a kind of cinema ticket or something. So you pay very little order today. Yeah.
Marco Liebsch, NSC. I have a question. So you addressed a lot of valid points like wireless coverage, bandwidth, as well as the support of variety of devices, including machine type. So I'm wondering if you see the 5G challenge only in the wireless, or how do you assess the role of the core network in the 5G adventure? I
should have included another picture here because when we talk about 5G, 5G is much more than just wireless. 5G is all the entire network behind, it's all it is about cloud, etc. The reason why I don't talk about it is I only know about the wireless side. But I mean, of course, major things will happen also beyond the wireless side. But my colleagues are much better than me on that one.
So I think that's all these requirements and the vision, what you laid down, is that if you were to say that 3 challenges in terms of realizing this vision, in terms of research, how you do tell 3 challenges are?
I think, I don't think I can come 3. I think, I mean, again, cost will be an extremely important thing. How are we able to provide all these services, all these bits, with all these very large number of base stations at a decent cost? I think, fundamentally, that's the key thing. I think that in some sense that's more important than everyone else, and we cannot. That's what kind of. Then we can say it's just energy consumption also thing, but I think fundamentally it's the cost. Then I think more technically, I think that traffic capacity and data that we know how to do this. I think this kind of reliability, for example, that's something which is much more. I'm not sure it's a bigger challenge, but it's something which is much more unknown to us. In that sense, it's very challenging because it's kind of a completely new area. So, I mean, we don't even know exactly what's meant by reliability, extremely reliable network. We have no clue how to do a network that's much more reliable today compared to today. So I think that's another area. I think, I mean, that's let's say, the fundamental thing I think is challenging, getting sufficiently low cost per bit. And about these other areas, I think the one that for me, let's say, is the biggest mystery is the reliability, because it's easy to write on paper, but it's really unclear even what's meant by it.
So do you include the availability within the reliability as
well?
Yeah,
reliability, availability, all these kind of things at the same time. Guaranteed that the connectivity is there with a certain quality when I want it. And truly guaranteed. It's not so that the operator can say, but I said it was 1% probability it will not be there. Yeah. Sorry?
I'll work on that, and we will distribute information on the attendees list, because maybe we can even distribute the video and everything. Yeah, but I need to talk to the guys actually, setting that up, because I'm not actually doing that. So yeah. Anyway, thank you very much.